Hello everyone, today we are going to look at the topic of generative adversarial network, also known as GANs. So first of all, let's look at the agenda. We're gonna look at some generative models, and we're gonna be revisiting the GANs. And there are three types of specific GANs that we will be talking about today, including WGAN and cycle GAN and star GAN. And for each type of GAN, there is going to be a code walkthrough for each one of them. So first of all, let's look at the generative models. So the very basic idea of a generative model is to learn the underlying distribution of the data. And after the learning, we can generate more data samples for this distribution. So so the motivation of this kind of network is just often the lack of the data points or the lack of data samples. So there are some examples of the generative models. The first one, probabilistic graphic models. The second one, Bayesian networks. The third one, variational autoencoder, which is also known as VAE. And I believe you have already been given a lecture on VAE. And the last one is the GAN network. Okay, so for generative models, the target or the purpose of us is to, there is a unknown distribution called PR, and then we also have a known distribution called P theta, and we want to make our P theta to get as close as possible to the PR, which is the real distribution. And there are two approaches to do this. The first one is to optimize P theta to estimate PR. And the second one is we can also learn a function g theta d, which can transform the d here into P theta. So the first approach is to optimize P theta to estimate PR, and for the divergence or for the distance, there are many kind of distance that we can choose. And the very famous one is our MLE here, and also the KL divergence. But notice that for the KL divergence, we have QX here, and since this is just our P theta, and which has a probability of has the value of 0, we want to add some random noises to the P theta to avoid the 0 values, which can lead to a explode of the KL divergence. And the second one, we can also learn the function g theta d. We want to learn the function g theta d, which can transform d to P theta. And d here is the known distribution like uniform or Gaussian. And we can try to train the g theta here by minimize the distance between g theta and PR. And again, there are many distance metrics we can use. For example, the KL divergence and also JS divergence, and also the Earthmover distance, which we'll be talking about shortly. And there are still many kind of distance that can be used. And okay, now let's revisit the GANs. So the GANs are generative models which will be trying to understanding the underlying distribution of the data samples, and we're gonna use this kind of distribution to generate more data samples. There are typically two networks involved in the GAN framework. The first one is called generator, and the second one is called discriminator. So the function of a generator, like it is introduced in the original GAN paper, is to generate some new objects, say the images or the audio files, the video files, from a random vector, which is just sampled from a noise basis. So if we want to combine the generator and the discriminator, we can say that the target of a generator is try to train a new object that can fool the discriminator, and respectively, the target of a discriminator is to not to be fooled by the generator. Its target or its purpose is to distinguish the synthesized images from the real images to tell whether an image is real or fake. So let's look at the training of a GAN framework. when we want to know a training process of a machine learning task, the very first thing is to look at the loss. So the loss of a gain is a maximum gain V here, and the target of the generator is to minimize the loss, and the target of a discriminator is to maximum the loss. So in this kind of situation, how do we gonna optimize this kind of objective function? So the way we do the optimization is to first we fix the generator, and then we update the discriminator, and secondly we fix the discriminator, and then we update the generator. So in this kind of setting, one very interesting thing is that in the just imagine in a general machine learning task, we can tell that the model is getting better if the loss is getting lower. But in this kind of training for GAN, one very a very possible thing for the training is we can say the loss can sometimes go higher and sometimes can go lower, just because we're training the generator or train the discriminator. So you cannot tell that the model is getting better or getting worse just by looking at the loss. So the very first loss we're gonna look at is the distance. Distance is the Earthmover distance, which is introduced in the WGANs. So the vector stand distance is nothing but the minimum energy cost of moving and transforming a pile of dirt in the shape of one probability distribution to the shape of another distribution. So to better understand the idea of the water stand distance, we're going to walk through a very tiny example here. We got P and Q here, which represent two different distributions. And there are 4 piles of dirt made up of, say, in total 10 shovelfuls for each of the distribution. And the target of us is to move one of them, say, or both of them, to make the 2 distributions to be all the same in the last. So let's look at how we do this. So in the first step, we can observe that the P1 here got 2 more shovelfuls of dirt. So the first thing we want to do is to move the 2 units of dirt to P2 here. So the P1 and Q1 got all the same. But again, we can observe that the P2 here got 2 more units of dirt than Q2. So again, we move the 2 units of dirt to P3. And at step 3, we can observe that Q3 here have 1 more unit of dirt than P3. So we want to move the 1 unit of dirt to Q4. So after this moves, we got the 2 distributions all the same. And in total, we move 5 units of dirt. So the vector stand distance in this kind of tiny example is 5 here. And then let's look at the objective function of the vector stand GAN. So one very important difference of a vector stand GAN is the loss of the discriminator. So we can observe that the discriminative loss is no more a direct quadratic, but this is trained to estimate the vector stand distance between the real and the generative data in the following formula. And again, the Lipschitz is clipped to 1, and this formula gives the formula of how we calculate the Lipschitz constant. But this point on the discriminator is not very good. This is just some empirical stuff. So instead, we clip the gradients. And here comes the gradient penalty of the vector stand GAN. So rather than constraint on the Lipschitz constant everywhere, we can just add some gradient penalty in the loss function in the LD here to make sure that the Lipschitz is almost 1 everywhere by adding this term. So when we are training the discriminator if we say if the gradient here is not 1, it's just some other constants, and if we have a very huge lambda here, so this term becomes very huge, so the loss will likely to become very huge. So when we are training the discriminator, it's just like say kind of move the gradient here to 0. But we do not constrain the gradients everywhere. We only penalize where there is a linear interpolation between the real and the fake data. So we do not use every x here. This is x prime, and this is just where there is a linear interpolation between the real and the fake data. Okay, and there is going to be a coding walkthrough led by Yash. Okay, and now let's look at the image translation. And the image-to-image translation often involves generating a new synthetic version of a given image. And let's just recall the very basic purpose of a generator is to generate some, say, new images from a latent space from the noise vectors. But now we do not want to generate from the noise vector. We want to do some translation task. So the input of our generator is an image. And here are some examples of this kind of task. If we want to change a summer landscape to a winter landscape, and if we want to do some modification to the human images, if we want to change the blonde to the black here, and also we can transfer an image to a painting style. And this kind of task often suffers from the very few data, because data for such kind of image translation is very limited or sometimes very difficult to generate. So this kind of task is often related to sort of unsupervised learning. So two variants of GANs are used for this specific task, the cycle GAN and the star GAN. So first of all, let's look at the cycle GANs. So instead of a single generator discriminator network, we have 2 generators and 2 discriminators. And one generator takes the images from the first domain and outputs the images from the second domain, from the domain we want. And the discriminator models are used to determine how plausible the generated images are and update the 2 generators accordingly. And the overall loss function for a cycle GAN is has some more terms than the original GANs, and this is given below in this formula. And the G and the F here are the 2 generators we have. Yeah, and the DX and the DY here are two discriminators we have. And appending to the 2 GAN loss, which is just like we said, max mean losses, we also have a term of called cycle consistency loss, and here. And notice this lambda. This is just to control how important the cycle loss is in this kind of loss. Now let's look at the framework and get to know how this kind of cycle GAN works. We got 2 generators here, G and F, and 2 discriminators, DX and DY, and 2 domains. The X domain is the domain of our input images, and the Y here is the domain we want. And so this is a cycle where we can generate the images in the Y domain by G, and also we can generate the X image back by using the F generator. And just notice that the G and F are different from each other, and so are the DX and DY here. So in the first loop, we can generate the image in the Y domain using G, and update the discriminator, update the generator using the discriminator Y, using the discriminator loss here, and again we can generate the X image back by using the generator F. So after we get the generated synthetic X, there is going to be a consistency loss. between the original input X here and the generated X. And if the two generators are very ideal, so the X here should be very similar, very close to the original input image. So this is the first consistency loss. And also we can do something oppositely. We can generate the X image from the Y domain and using F here. And then again, we can generate the Y back using the G here. So there is again a consistency loss between the Y we generated and the Y as a original input. But in practice, in the real world training, as just imagine that we want to translate an image to the painting. So we do not really get the painting of the image. So sometimes these two loops, we can only use one of them since we do not have the say the original Y image here. And for the cycle consistency loss, we're using the F1 loss here. And this is also some empirical choice because F1 loss here in the GAN training often performs better than the F2 loss, than the L2 loss. Okay. And there are many applications for the cycle GAN, like style transfer. We want to transfer the input images style to another kind of style, say Van Gogh or something else. And also we can do the objective transfiguration. We want to transfer a horse to a zebra or something like that. We want to or we want to transfer a zebra back to a horse, and this can be done using the cycle GAN. And appending to this, actually, cycle GAN has a very wide use in the GAN framework training, because just like intuitively, a generator should be able to generate the original input, say audio or image back, if the generator's function is very good. So if you want to train a GAN framework, just consider using the consistency loss anytime you want to train a GAN framework. Okay, so now let's look at the star GAN. So what star GAN does is to help us to generate images in the target domain given an input and the target domain. So for example, we're given an image of a man and the target domain is gender. So we want to know how this man would be looking like if he was a woman. And the second example, we're given an image of a person and the target domain is age. So this kind of tasks are often, again, related to the unsupervised learning. And how we do this, introduced by star GAN, is that we train the generator discriminator framework in the adversarial fashion like we did before. And there is an additional classifier. So along with the normal loss, there is an additional term of the classification loss while we're training the generator and the discriminator. So we're going to interpret the star GAN using a very tiny example. So we have an image of a boy who is 10-year-old, and we want to know how this boy will be looking like once he is, say, 20-year-old. So the target domain here, the target domain is 20-year-old, and this is the input image. And the original domain is 10-year-old. So the generator should be able to give us a fake image by our given input image and the target domain. So the fake image should be looking like a 20-year-old man, right? So so there is a reconstruction loss, which is to say, if we are given the fake image who is likely to be 20-year-old, and we have the original domain who is 10-year-old, the generator should be able to give us our reconstructed image who is 10-year-old boy, and it should be just the same as the input image. So again, there is a reconstruction loss between the reconstructed image and the original input image. This is something very similar to the consistency loss we have introduced just now. And what's very important here is the classifier. So the original discriminator just do the real or fake classification. We're giving a fake image, which is the same fake image here, just given by the generator. And the original discriminator's task is just to tell whether the image is real or fake. And now, besides the real or fake task, we also want to tell, is this fake image, so what's the age of the fake image, right? So the objective function of the generator here is the adversarial loss like we introduced before, and a classification error, a classification loss, and a reconstruction loss here. And also our discriminator has two objectives. The first one is to tell whether the generated image is fake or real, and the second one is what is the domain in which the generated image belongs. So if the generator is able to generate some images to fool the discriminator, then the discriminator would predict the target domain, and then we stop training. And look at the objective function here, the LD here, and why we add in a minus here is just because we want to say minimize the classification error, and we want to maximize the adversarial loss, because we really want to tell if the generated image is real or fake. And this is just the original task of a discriminator. And the application of a star GAN can be very wide. So we're given an image and we want to say how he will be looking like if he had blonde hair, and he was a woman, he was growing, and he had pale skin. And you can tell that this is just some very unsupervised task, because you will never get to know how this man will be looking like if he was a woman, right? So StarGAN really give us a very good framework for the unsupervised learning of a image translation task. Okay, thank you very much. And again, Yash will be walking through the coding part of the cycle GAN and StarGAN.
Hi, I'm Yash Bele. Welcome to the recitation on GANs. In this part of the recitation, I'm going to be walking you through the code for how to implement the various GAN loss functions and how to write the entire training setup for GANs. Let's start off with how we write the loss functions for GAN. Before I actually jump into this section though, I want to introduce you all to some notation that I'm going to be using in the rest of the slides. GANs are essentially a generative model that draws samples from a distribution of our choice. We're going to be calling this distribution as P of X. In our case, we're going to be talking about distributions over images. So P of X for us will denote a distribution over all of the possible real images that we want to model. Next, we're going to talk about P of Z. This is the distribution over the generator's input. This could really be any distribution of your choice. It could be a uniform distribution between 0, 1, or it could be a standard normal distribution, or really anything that you choose. The next important part that we're going to be looking at is the generator itself. We're going to be denoting the generator by the symbol G. In our case, the generator takes as input a noise vector Z and outputs an image, which we will denote by G of Z. The generator is typically a convolutional neural network. The next neural network that we are going to be looking at is a discriminator, which we denote by the symbol D. The discriminator takes as input an image and outputs the probability that the image is real. Hence, the discriminator's output lies between 0 through 1. We're going to be denoting the labels for real images by 1 and the labels for fake images by 0. This means that if the input to the discriminator is a real image, ideally we would want the discriminator to give an output of 1 for that image. And if the input was a fake image, we would want the discriminator to give an output of 0 for that image. Next, let's look at the GAN loss function. The loss function for the GAN is set up as a minimax game between the generator and the discriminator. The first term is an expectation over the distribution of all of the possible real images, and the second term is an expectation over the distribution of all possible fake images. The discriminator tries to maximize this loss, whereas the generator tries to minimize this loss. Let's try to simplify this expression a bit. We can write the expectation over the real images as a sample average over the real images, and we can also write the expectation over fake images as a sample average over the fake images. Let X be a mini batch of real images drawn from P of X, where the cardinality of X is n, and Z be a mini batch of samples drawn from P of Z, where the cardinality of Z is also n. We can then write our GAN loss function in the following format, where we've essentially just replaced the expectations by sample averages. Next, let's write the loss functions for the generator and the discriminator separately so that we can iteratively update them one by one. Notice that we have a maximization over the discriminator. However, whenever we're normally optimizing neural networks, we're minimizing a loss function. So we can write the maximum over this loss function as the minimum over the negative of this loss function, as you can see on the next slide. So the discriminator loss is now the minimum over the sample average of the log of d of x over the real images and the sample average of log of 1 minus d of g of z for the fake images. Let's look at each of these terms separately to see what they each denote. The first term is the cross entropy between the predicted labels for the real images and the true labels, which is 1. This means that the discriminator is trying to predict 1 for all of the real images. Similarly, the second term is the cross entropy between the predicted labels for the fake images and the fake labels, that is 0. This means that the discriminator is trying to predict the label 0 for all of the fake images. So the overall discriminator loss function tries to simultaneously predict 1 for all of the real images and 0 for all of the fake images. When we write this out in terms of code, we have two parts of this loss. The loss over the real images is simply a binary cross entropy loss over the predictions for the real images and their corresponding labels, which are 1s. And the loss for the fake images, which is simply the binary cross entropy loss for the fake images and their corresponding labels, which are 0s. Next, let's take a look at the generator loss. Next, let's take a look at the generator loss. The generator loss is of the form shown here. If we observe the two terms, the first term doesn't really depend upon the generator. This is because it's simply the prediction of the discriminator for all of the real images. The generator has nothing to do with it. The generator only generates the fake images. So when we're trying to maximize this overall sum of terms with respect to the parameters of the generator, the first term will always remain unaffected. So we can throw it out of the optimization. This in a sense is just an optimization over the second term. Now the maximum can be written as negative of minimum leading to this formulation. This looks pretty similar to the discriminator loss that we saw before. This is simply the negative cross entropy loss between the predicted labels for the fake images and the fake labels. This makes sense as the generator does not want the discriminator to predict the fake label for the fake images. It wants to fool the discriminator as much as possible. When we write this in terms of code, we simply have the negative of the binary cross entropy loss between the fake images and their corresponding fake labels, which are zeros. If you noticed, however, the generator loss has a subscript SAT. This stands for saturation, which leads us to our next slide. There are a few practical problems with the current form of the generator loss. When the discriminator is confident that the fake images are indeed fake, d of g of z goes to 0. Often enough, when you're training, during the initial phases, this is indeed what happens. When this happens, however, the gradients received by the generator tend to 0. As a result of this, the generator parameters really don't update much, and the GAN isn't able to learn to produce any sort of realistic looking images. The GAN training fails in that case. In order to overcome this problem, there is a heuristic different loss that we use for the generator that tends to work well. All we do is we simply change the log of 1 minus d of g of z with the negative of log of d of g of z. This loss has a simple interpretation too. This is simply the cross entropy loss between the fake images and the real label. In terms of code, it's simply the binary cross entropy loss between the generated images and the real labels. Now, let's take a look at the overall code setup for our GAN training. First, we define our generator and then we define our discriminator. The loss function that we're going to be using throughout is a binary cross entropy loss. We have two separate optimizers, one for the discriminator and one for the generator. First, we draw a sample of the random z vectors. Next, we get a set of x's from our training dataset. To update the discriminator, we first compute its loss on the real images, which, as we've seen before, is just the binary cross entropy loss between the real images and the real labels, which is ones. Next, we compute the discriminator's loss on fake images, which in turn is just the binary cross entropy loss for the fake images, for the predictions for the fake images, and the labels for the fake images. The overall loss for the discriminator is just the sum of these two losses, and then we optimize over this loss. Remember that in our modified generator loss, what we were trying to do was trying to make the discriminator think that the fake images are real. This in turn was just the binary cross entropy loss between the predicted labels for the fake images and the real labels. And then we essentially just optimize over the parameters for the generator. Notice that in the first half of our code, where we are just optimizing the discriminator, we're only updating the parameters of the discriminator. Similarly, in the second half of our code, where we are optimizing the generator, we're only updating the parameters of the generator. You need to make sure whenever you're implementing GANs that you have separate optimizers for the discriminator and the generator, so that you don't end up changing the parameters of the discriminator during the generator update and vice versa. Next, I'm going to walk you through some of the typical GAN training code. I'm only going to take you through some of the important parts and just walk you through some of the typical generator architectures, the discriminator architectures, and the things that you should look out for. As you can see in this code over here, we have a simple generator that is a fully a, a fully connected neural network. It has four layers, as you can see. It starts with the input noise vector and goes through a bunch of linear transformations, followed by a batch normalization layer and a nonlinear transformation, which is a leaky ReLU for us. At the very end of the neural network, we produce an output that is of the size of the shape of the images that we want to generate, as you can see here. For MNIST images, this would be 28 cross 28. Next, we squash the outputs to lie between -1 through 1 using our tanh activation. This is also something that we do because our inputs to the discriminator are processed in such a way that they should always lie between -1 through 1. Next, let's look at a typical architecture for a discriminator. As you can see, the discriminator 2 is a very simple neural network. It's fully connected to. It starts with a linear layer that accepts the entire input image that is flattened out, followed by a leaky ReLU layer and a bunch of other linear layers. At the very end, we have a single neuron output for this discriminator, which is then passed through a sigmoid function. This essentially just denotes the overall probability that the discriminator is assigning to the output, to the input. Remember that we want this probability to be 1 for real images and 0 for fake images. There's a special reason why we use the leaky ReLU activation in the discriminator. If you use the normal ReLU activation, it's quite prone to the gradients dying out before it reaches the generator. And when that happens, the generator isn't really able to update very well, which is why we tend to use the leaky ReLU activation with the discriminator. We define the adversarial loss function as simply the binary cross entropy loss. Let's move down to the training loop. Now we define the optimizers for the generator and the discriminator separately. Remember, it's imperative to do it in this way so that we do not update the discriminator weights accidentally while trying to update the generator and vice versa. For each batch of training inputs, we create a set of real labels which we denote by valid, and we fill them with the value 1. Similarly, we create a batch of fake labels and we fill them with the value 0. Next, we get the real images, which are essentially just images from our training dataset. In our setup, we're first going to be training the generator. We first sample a bunch of random noise vectors z, and we generate the images corresponding to these noise vectors. Remember that in our modified loss function for the generator, we wanted to try to make the discriminator think that the generator was predicting real images. So this is just the binary cross entropy loss function between the prediction over the images generated by the generator and the labels for the real images. Notice that your generated images are generated through your generator. When we're trying to optimize this entire setup through gradient descent, the gradients will first be computed with respect to the loss function passed through the discriminator and then into the generator. Since the discriminator's weights are not being updated in this step, only the generator's weights will be affected. However, we still do need to compute the gradients with respect to the discriminator so that the generator's gradients can be computed. Next, we'll look at training the discriminator. We first measure the loss for the discriminator for the real input images. This is simply the binary cross entropy loss between the predicted labels for the real images and the true labels, which are ones. And for the fake images, this is just the cross entropy loss between the fake images and the fake labels. And the overall loss is just an average over these two losses. And that's all you need to train a basic GAN. We're next going to look at the WGAN formulation, which allows us to generate even better images. Now, let's take a look at the WGAN setup. Much like the regular GAN loss, the WGAN loss is also simply just a minimax over the generator and the discriminator. However, unlike the typical GAN setup, the expectation terms no longer have a log inside of them. This means that the discriminator no longer predicts a probability for the image being real or fake. Instead, it predicts a score for the image being real or fake. Ideally, the discriminator would want to predict a score of positive infinity for real images and negative infinity for fake images. The only constraint in this overall setup is that the discriminator must be K-Lipschitz continuous. We'll talk about how we enforce this K-Lipschitz continuity in the discriminator in the further slides. The WGAN loss essentially just measures the Earthmover distance between two distributions. The two distributions between which the generator wants to minimize the distance between are simply the distribution over the real images and the distribution over the fake images, denoted by P of x, and the induced distribution over P of z as is, after it passes through the generator G. So let's talk about how we essentially enforce the K-Lipschitz continuity for the discriminator. A simple method proposed by the authors is to simply clip the weight of each weight within the discriminator so that the absolute value of these weights is less than some constant c. Is this really a good way of maintaining Lipschitz continuity? The answer to that question is no. As acknowledged by the authors in their paper itself, this doesn't really enforce Lipschitz continuity very well, and it has a bunch of other negative side effects. However, in practice, it does seem to work somewhat well. Next, let's take a look at how we can simplify the WGAN loss. The WGAN discriminator loss can be written in the following form. Here, we simply replace the expectation over the real images and the fake images as expectations over sample averages of the two. Next, we write the maximum as the negative of the minimum. And this is the final form of the loss for the discriminator. In terms of code, we can write this very simply as just the negative of the mean over the discriminator's predictions for the real images and the mean of the discriminator's predictions for the fake images. Once again, the discriminator wants to predict high values for the real images, so the negative of that would essentially give us a low discriminator loss, and the discriminator wants to predict very low values or negative values for fake images, which would in turn also give you a low discriminator loss. The other thing that we need to look out for is to make sure that our discriminator is Lipschitz continuous. As mentioned in the previous slide, we do this by clipping the absolute values of each of the weights in the discriminator to be less than some predefined constant c. We can implement this in terms of code through this very simple formulation shown below. Next, we're going to take a look at the generator loss in the WGAN setup. We can use a similar argument as we presented for the regular GAN generator loss to get rid of the first term, as it really doesn't depend upon G. Now, the loss for the discriminator can simply be written as the negative of the average over the scores assigned for the fake images. We can write this very simply in code. Let's try to think about what this loss really means. The generator wants the discriminator to assign high values for the generated images because high values correspond to real images. And that's really why the loss is of the form that it is here, as we can see here. Here's a rough code implementation of the overall WLAN setup. In the first two lines, again, we just define the generator and the discriminator. C is the overall clamping constant that we use. Next, we again define separate optimizers for the discriminator and the generator. We also get a batch of latent vectors Z and a batch of training data X. Now, to compute the discriminator loss, we essentially just compute the negative of the mean over the scores assigned for the real images and the mean over the scores assigned for the fake images. We then optimize the discriminator. As soon as we've optimized our discriminator, we want to ensure that it is still Lipschitz continuous. And we do this by essentially just clamping the weights between negative C and C. Now, to update the generator, we just compute the negative of the mean over the scores assigned for the fake images and we optimize over it. Next, we're going to take a look at a complete implementation of the WLAN setup. Now, we're going to look at the code to train a WLAN. The setup is really similar to the setup that we had for training a regular GAN. All that has really changed is our loss function. Our generator remains the same as we had before. It's just a simple fully connected neural network that outputs an image between -1 through 1. Our discriminator also has the same setup as before. It too is a fully connected neural network that takes an image and produces a single output. Notice, however, the one small change in the discriminator architecture. For our regular GAN, we had a sigmoid activation function, so the discriminator predicted values between 0 to 1, which were just probabilities that the image that the discriminator had seen was real. We don't have that sigmoid anymore. This is because the discriminator now predicts scores, which are any sort of real valued numbers. We predict higher scores for real images and negative scores for fake images. Next, let's take a look at the training loop. The optimizers that we have remain the same as we had in the earlier setup. The only thing that has really changed is the loss functions. Now, the loss function for the discriminator computes the mean over the predictions for the real images and the predictions for the fake images. Notice that we don't have any sort of cross entropy loss or anything else at this point. It's simply just a negative over the mean of the scores for the real images and a mean over the scores for the fake images. Next, we enforce Lipschitz continuity by clipping the weights of the discriminator over here. To update the generator, all we do is optimize its loss function, which is just the negative over the mean over the discriminator's predictions for the fake images, as you can see here, and we then optimize the generator. So that's it for this recitation. I hope you learned a little bit about how GANs are implemented in code. You can use this reference code to try to build your own GAN model and see what kind of results